Hi, in this video, we want to take a look at bootstrapping autoregressive time series models, specifically the coefficients. Okay, so why am I talking about this? Well, bootstrapping, a well-known method in statistics, gives us tools to do deeper analysis on our data that uh, that, that can fill in the gaps when the theoretical constructs and assumptions may not hold for what we're working with our real life data. And so typically we use Bootstrap when the theoretical assumptions needed for classical statistics don't hold out. Like I look at my data, I look at what I've got, I look at the theoretical assumptions, I go, they don't match up. All right, what do I do? Well, one approach is to use bootstrapping. Now, the big idea with bootstrapping is that we are going to sample with replacement observations that we have independently, identically distributed, IID. All right, so now think about autoregressive time series. Autoregressive immediately means we do not have independence. So how can I possibly do bootstrapping when I need independent, identically distributed sampling with replacement of my observations? How can I do that with autoregressive, which by definition is not independent? Our trick here, we're going to do our sampling on the residuals. And that's the big one of the big punchlines of this video. All right, so let's go ahead and start working through our code, working through our example. First, we're going to load our data and set up our workspace. Here, I'm just suppressing the number of digits printed. Here, I'm saying avoid scientific notation if you can. And we're going to go ahead and use the recruitment time series data from the ASTSA package. All right, so now what we're going to do to be able to get to the bootstrapping is that we're first and foremost going to fit an autoregressive model. Now, if you've been watching my other videos, if you've been checking out lectures in my class, you know that the recruitment time series data is appropriate for a degree 2 autoregressive model. All right, so we'll use the Euler-Walker estimation process to get our coefficients. Notice that I am setting the order max to 2, and the system will take and fit degree 2 and keep it there. Now, if I was to put AIC equal to false, what it will do is it will stay with the maximum order I put in automatically, and it'll stay put. If I put AIC equal to true, it's going to go and it's actually going to check to make sure that this is the correct order. And so let's say I told it 5, and the model should, the diagnostics say it should be a 3. Well, then R would automatically trim it down if AIC is equal to true. If it's equal to false, it'll keep it where I want it. So I put it to true, and I'm still going to get a degree 2 model because it's a good fitting model. All right, so now let's say I'm in a situation where for some reason I don't trust the regular statistics approach for my autoregressive model. I either an assumption doesn't hold out for me, maybe I don't like the fit, maybe I want to dive deeper into a feature of the model that we don't have a theoretical aspect for. That's another aspect of bootstrapping that we can use, is that we can figure out distributions of statistics from our models that we can't get distributions for otherwise. All right, so how are we going to do this? So bootstrapping, we need independent, identically distributed sampling with replacement on my observations. So in bootstrapping, I'm going to, let's say I have 100 observations. I'm going to take sampling with replacements, 100 of those observations. So when I sample with replacement, some of them are going to will be picked up multiple times. Some will be left out in this resampling process. All right, so I'm going to pretend that this resampled sampling with replacements on my observations is my true legit data. Then I'm going to compute what I'm interested in. Then I'm going to repeat the sampling, compute, sample, compute, sample, compute over and over and over until I get a distribution of the statistic that I'm interested in. Now, this is well and good. I just need to have something to sample with replacement independently, identically distributed. All right, well, how am I going to do that? Well, we're going to take the point of view, we're going to make the assumption that the residuals are independent and identically distributed themselves. So we know that the time series values are not, but we're going to go ahead and assume that the difference between the model and the observations, that those are independent, identically distributed. With that, boom, I can do the bootstrap. So what we're going to do is I'm going to do that bootstrap sampling on the residuals from the model. All right, so then I'm like, well, how can I use that to get statistics? Well, here's that trick. And this is from the textbook that I'm teaching from right now. I got this idea from them. What we're going to do is we're going to take these residuals, we're going to sample with replacement. So here's the sample portion of the code. I'm going to sample with replacement. I'm going to simulate an AR2 model with the same coefficients that I actually fitted a moment ago. So this is a little bit different than like other bootstrap things, like other bootstrap approaches. We don't want to use computed values directly in our process, but for us to be able to do the simulation, we need some value to kick this off. If I didn't have some value to kick it off, I couldn't get the simulated value. So this is the best that we can do. And so you'll notice that I'm taking the mean from my data set. This is actually the mean of the time series. And then I am running a simulation on this. So here, this is the simulated values. I'm putting in the coefficients I've got fitted, random sampling of the residuals with replacement, and then run a simulation to get a simulated time series. Then, with the simulated value, I'm going to go ahead and fit the coefficients. Now, I'm going to do this sample, simulate, fit, sample, simulate, fit, sample, simulate, fit over and over and over. In fact, I'm going to do it 10,000 times. All right, and then as I do this, I'm going to get a collection of models that hopefully have the same distribution of the model that I actually fitted. And this collection of models will give me inference about what's going on in the process I'm working on. Now, one thing that you'll notice when you look at this code, you'll notice that I'm dropping the first two terms in the residuals. Why is that? Well, remember that's a degree 2 model. I fitted a degree 2 model. And so because of that, the first two values are treated as constant values, and the residuals are in A, so it doesn't make sense. And so my simulated time series are two values shorter than the original time series. Now, if you didn't like that, you could do like backcasting or something like that to fill in those first two. I went ahead and dropped them and just proceeded forward with that. So you could argue in a small sample situation that we could have a different distribution when sample size is part of the parameter for the variance or the standard error of estimates. But I think it's not much of an issue on this case. All right, so now after I've got all these models built, I'm going to extract the coefficients. And so that's the AR portion of the model. To do this in a very quick and efficient way, I'm going to use the sapply function. Now, I could have done this in a for loop, and a lot of programmers prefer for loops, but remember, for loops are slow in R. the sapply, lapply, apply functions are usually faster than a for loop. Now, here I'm extracting. Now, the format is not exactly the way I want. It's actually the transpose of what I want. So I go ahead and take the transpose, and that's going to be all of my coefficients. And it's not quite a data frame yet, so I go ahead and convert it over to a data frame, and then I assign the column names. And so here, from my bootstrap, I get a range of values. So I see phi sub 1, phi sub 2, and we see for phi sub 1, it's about 0.11, or sorry, 1.1 and 1.5. For phi sub 2, it's going from negative 0.6 to negative 0.2. Okay, so there we go with that. Now let's go ahead and visualize the empirical bootstrap density that I've got. So I want to see what, if I want to do hypothesis testing, or I just want deeper inference on what's going on, I want to do visualizations. Always, always, always use visualizations. So I'm going to use ggplot, and I'm going to plot all of the coefficients I've got using GM points. I'm going to take all those points and get a, so I've got 2 dimensions. So I'm going to get a 3-dimensional curve where I have the phi1, phi2 are the first 2 dimensions. The third is going to be the height of the probability distribution function that I'm estimating. And then here, I'm going to put down a red dot to indicate the mean of phi1, phi2 from the bootstrap simulation. All right, so now when I look at this, so each individual bootstrap iteration has 1 dot, and you'll notice I made the dots transparent so that when I put them on top of each other, the darker regions indicate where we have more points. All right, so we can see that there's kind of like an ellipse shape going on. Now, you'll notice that there's a little bit of wiggle in these ellipses. These are not perfect ellipses. Why? Because this is off of empirical data. Now, something else that jumps out at me is that this dot is not perfectly in the center. Okay. And there might be a little bit more observations over here than over here outside of this last largest ellipse. Okay. So, some things to think about. Now, I mean, that looks pretty close to normally distributed. So that might be a reasonable way to go with, to say, hey, I have bivariate normal distribution of the coefficients. And if this is correct and I go with this can give me deeper understanding and can set up like hypothesis testing and other statistical things I can do. Now, another way I can go about this is, well, if everything goes according to theory, I would be getting a bivariate distribution off of these two in the asymptotic distribution. So the asymptotic distribution for autoregressive coefficients are multivariate normal asymptotically. So that's when I say asymptotic, I mean when I have a large enough sample size, the distribution will get super, super close to being multivariate normal for all my coefficients. All right, so what I'm going to do is another option I have when I do bootstrapping is to not get the empirical distribution, but to go ahead and use my bootstrap iterations to estimate the parameters of the density that I should be getting. And that's what I'm going to do here. And so what I'm going to do is I need to use the MT norm package to get the density of the bivariate normal distribution. Now, to do this, I need to specify what points on the 2-dimensional plane I'm going to drop in for that bivariate normal. And well, here I'm going to use expand grid to work that out. And so here we're taking 200 phi1 values, 200 phi2 values, using expand grid to go through all the possible combinations, all the possible pairs. Then I'm going to fit the density, and we go at all the points of interest. I'm going to get the height of that bivariate probability distribution function. And so here, when I do that bivariate normal, it's multivariate normal, but 2, so it's bivariate. The column means are going to be my estimate of the center. So the mean of the phi 1s, the mean of the phi 2s are my estimate of the center of the normal distribution. And I'm going to use the covariance of my bootstrap iterations to tell me what is the sigma for this distribution. And so once again, I'm going to go ahead and plot it, and I want to see what's going on. I want to take a look. All right, so now you'll notice that the curves are perfect ellipses now. All right. Now, the dot is perfectly in the ellipse. That's by construction. It has to be that way. Now, when I look at this, I notice I do have more points kind of trailing off here. So it's possible that maybe the normal distribution isn't quite right. It's pretty close. I would honestly go ahead and just go with normal distribution. I feel like it's a good way to go with on this particular data set. But I can know in the back of my mind as I proceed, it's not quite right, but up to the level of human interaction with theoretical mathematics, it's close enough. Now, what we can also do, we can take the pencil and paper theory from the proofs and take the asymptotic distribution that we would get if the theory and the assumptions are correct, connected to the generation of the data, and we had a sufficiently large sample size. All right, well, to do that, I'm going to go through the same game plan. Once again, I'm going to use the multivariate normal distribution. And I picked this particular model with 2 coefficients because we can visualize it. If we had 3, 4, 5, 6 coefficients, we could run through this using a pairs function, by the way. And we could do multivariate normal very naturally off of this. All right, and so what I'm going to do, I'm going to plot my points from my bootstrap once again. I'm going to plot down the contours that are from the theoretical asymptotic normal distribution. And then I'm going to put down the fitted values of that model we have. So the models, phi 1, and the models, phi 2. Let's take a look. All right, so now, so we have ellipses once again, and we notice it's a little bit tighter than we had before. And we've even got some more bootstrap values that are on that lower left-hand corner side of the ellipse. And so this might be a little bit off. I would still proceed with the pencil and paper assumption proofs, by the way, off of this. I don't think there's enough of a deviation. But if I was doing bootstrap, potentially I could see something grossly different than what the theory says I should be getting. And if the theory is different, then I know that one or more of the assumptions is not holding for the situation I'm in. Now, one thing I want to point out about this is that on all 3 of these, we notice that we have a negative slope if I visually put on a line of best fit on these dots. Why is that? Well, think about that data that we have. If I was to take the original data and I went ahead and increased phi 1, well, to get the model to fit reasonably well, phi 2 would have to decrease. Now, if I decreased phi 1, phi 2 would have to increase to compensate. And so there's like a balancing act there. And this line here shows that balance right there, that we can see that if we were to increase phi 1, the slope of the line passing through here indicates on average how much we would expect to see phi 2 decrease. All right, well, that's all I've got for you. Life is short. Do math.